Welcome to this explainer. Today, we're going to demystify the invisible mechanics that make everyday internet tasks like simply sending an email actually function. Think about it. Every single second, millions of terabytes of data are routed across this chaotic, globe-spanning web of cables and servers, usually in mere fractions of a second. Have you ever hit send and just wondered how your message navigates all that digital madness to land perfectly in a friend's inbox? Well, today, we are pulling back the curtain on the protocol stack to show you exactly how this brilliant system manages that incredible journey.
Here's our agenda for today. 1. Meet the application layer. 2. How email works, specifically looking at SMTP. 3. Enter the transport layer. 4. The TCP three-way handshake. And finally 5. TCP versus UDP protocols. Let's get right into it.
Section 1. Meet the application layer, the top of the protocol stack. So this is the layer closest to us. It acts as the ultimate translator between human intent and raw network data. It utilizes all the services of the underlying layers to perform the functions we actually care about, like file transfers and web browsing. Now, this layer is home to a massive suite of really powerful protocols. Take DNS, for example. DNS is essentially the internet's giant high-speed phone book. Instead of forcing you to memorize long, clunky strings of IP numbers just to pull up a website, DNS seamlessly translates a human-friendly address, like google.com, into the exact numeric IP address the network needs. Then there's SNMP, the Simple Network Management Protocol. You can think of SNMP as the digital nervous system of the entire network. IT administrators rely on it constantly to monitor router health, track bandwidth, and detect failures before a network completely crashes. These protocols are working silently, 24/7, just to make the internet usable for us.
Now, most applications operating in this layer rely on the client-server model. In this setup, your computer or your phone, that's the client, initiates a specific request, and a powerful always-on server sitting somewhere in a data center processes it and returns a response. Think about checking your bank account online. Your browser acts as the client, basically knocking on the bank's digital door to request your financial data. The bank's web server, which has to be running all the time, processes that authentication and securely sends your balance right back. It's just this continuous, structured request and response loop.
Moving on to Section 2. How email works, the simple mail transfer protocol.
Let's map out the precise journey of an email from user 1 through their local mail server, across the internet via SMTP, all the way to an organization's destination server. When you compose an email, your message doesn't just beam straight to your friend's laptop. There's no magic there. Instead, it gets handed off to a piece of software called a Message Transfer Agent, or MTA. Think of the MTA as a highly efficient digital post office. It receives your raw message, inspects the destination address, sorts it, and then determines the absolute best route to move that mail toward its final destination using SMTP.
Notice how the Simple Mail Transfer Protocol doesn't just wildly fire your message into the void, it actually sequentially queues the data at your local server and actively relies on a dedicated TCP connection to make that jump between servers safely. Have you ever noticed that if your Wi-Fi drops right after you hit send, the email just sits there patiently in your outbox? Well, this is exactly why. It's literally waiting for that dedicated TCP connection to be firmly established before it even attempts to leap across the web. Once that connection is secure, the message traverses over to the recipient's mailbox, just waiting for them to open it.
All right, Section 3. Enter the transport layer, the invisible engine moving your data.
Even though application processes on different hosts aren't physically connected to each other, the transport layer provides a logical, two-way communication pathway between them. Look at how the transport entity sits directly between the application layer above it and the network layer below it. This distinction is absolutely crucial. Down in the network layer, routers are just bouncing packets from hop to hop in this chaotic, best-effort scramble. But the transport layer? It's implemented purely in the end systems. It essentially creates a serene, invisible, end-to-end tunnel specifically for your application's data, totally isolating your software from the physical chaos going on in the network beneath it.
To achieve that reliable data transmission, the transport layer has to juggle 5 critical elements simultaneously. It has to perfectly manage addressing to find the right application, handle connection establishment to securely open a session, and utilize flow control so a lightning-fast sender doesn't completely overwhelm a slower receiver with a massive tsunami of data segments.
Let's focus on addressing for a second, because this is a really vital distinction. Think of an IP address as finding the correct physical building, but the port number acts as the specific apartment number inside that building. When a server receives a data packet, it looks at the 16-bit destination port number embedded right in the header.
That specific number tells the server exactly which running application, whether it's your email client on port 25 or your web browser on port 80, should be handed that specific piece of data.
Which brings us to Section 4, the TCP three-way handshake, establishing a reliable connection.
Because the internet is vast and, honestly, pretty unpredictable, it can delay packets for incredibly long periods of time. So a simple hello just isn't enough to start sending sensitive data. The transport layer needs a foolproof way to verify that a connection request is actually current and valid right now. Imagine getting a hello text from a friend that was somehow delayed by a broken cell tower for like 5 whole years. You wouldn't want to blindly reply and start a deeply confused conversation. Well, the transport layer relies on a synchronization procedure to prevent exactly that kind of ghost connection.
The brilliant solution to this problem is the TCP three-way handshake. You can think of it as a strict, human-like call and response. The initiator starts by sending a SYN request, which essentially asks, "Hey, can we talk?" The responder receives it and replies with a SYN-ACK confirmation, meaning, "Yes, I hear you. Can you hear me?" Finally, the initiator sends an ACK, confirming, "Yes, I do. Let's begin." This elegant three-step dance ensures both machines are fully synchronized in the present moment. It completely guarantees that no combination of old, delayed segments can ever trigger an accidental connection.
Once your data is successfully transferred, that connection must be formally released. Now, this can happen asymmetry, which is kind of like abruptly slamming down the telephone receiver mid-sentence, or symmetrically, where both sides politely say goodbye. In a TCP connection, a graceful symmetric release is almost always used. The client sends a FIN segment to signal it has no more data, the server acknowledges it, and then the server follows up with its own FIN segment. Both sides literally have to mutually agree that the data transfer is completely finished before that invisible tunnel is finally collapsed.
And finally, Section 5, TCP vs UDP protocols, choosing the right transport for the job.
When you look at the broader architecture, the transport layer actually offers two very distinct protocols for moving your data, TCP and UDP. TCP is deeply connection-oriented. It requires that elaborate handshake we just talked about to guarantee delivery and perfect data ordering. UDP, however, is entirely connectionless. It skips the handshaking dialogue altogether. UDP is inherently unreliable. It strips away flow control and error checking in favor of raw, unadulterated speed.
A good way to think about it is TCP is like a careful, meticulously tracked conveyor belt. If you're sending a critical email via SMTP, TCP ensures every single letter arrives perfectly in order because, let's face it, a corrupted email is entirely useless. But UDP? UDP is like strapping your data to a rocket. If you're streaming a live 4K video or making a voice call, UDP is the undisputed champion. It happily accepts that dropping a few frames of video or a single millisecond of audio is a perfectly fine trade-off to keep the live stream moving forward in real time, completely free from the sluggish lag of retransmitting lost data.
Understanding these invisible layers empowers you to see the internet not just as digital magic, but as a brilliant, highly structured system of protocols working tirelessly behind your screen. From the top-level application requests, managing DNS, down to the meticulous routing of transport ports and handshakes, your entire digital world relies on this precise choreography. So the next time you hit send or start a video call, ask yourself, is your data taking the reliable TCP train or the speedy UDP express? Keep wondering about the hidden engines powering our connected world.